Okay, we're back talking about where we're going to protonate 1-butene. So I'm going to draw a more complicated energy diagram here. So we'll go with energy on the y-axis, and I'm going to put my 1-butene plus HCl in the middle here. And so the reaction progress is going to go sort of in both directions. You'll see in a second. So if I protonate to form the primary, if I protonate to form the secondary cation, that species has some energy there, okay? And then that can go on to products, and that can form then the more substituted alkyl chloride. And notice I'm not drawing mechanism on these diagrams. We typically don't push electrons on these diagrams. Just gets too complicated. But I'm going to then connect these with my saddles, something like that, okay? So the alternative pathway will be protonation at the internal position to generate the primary carbocation. And we know from that list that I gave you that that is the higher energy intermediate. So that has got to be somewhere up here, okay? And so that will go on to product then, and in this case, it will be the linear or less substituted product. And so I'll connect these with saddles like that. Oops, where did that go? Okay, something like that, all right? And the key point is that the activation energies for these two processes are different. So this is the delta G double dagger. We can call it for the secondary cation. And this is the delta G double dagger for the primary cation, okay? And so if you remember back on that rate expression I gave you, the rate of a reaction is directly proportional to delta G double dagger. As delta G double dagger increases, K gets smaller. And so the faster reaction, the one that's more favorable, is going to be the one that proceeds to generate the secondary carbocation, okay? And that then leads to an important point, which is we can define a delta G here. Okay, and delta G is the difference in energy between the transition states, and this defines then the ratio of products. Okay, and so in essence, just a couple kcals of energy difference, delta G is bigger than 2 or 3, you have a sort of a 10-fold, 10-to-1 ratio of products, all right? And so we then want to talk about sort of what, the one thing we haven't gotten into is what are these transition states that I've mentioned, you know, the TS, so call this TS secondary, TS primary. We haven't really talked about what they look like or, you know, their geometries and things. And so that's where we want to introduce what is known as Hammond's postulate. And hopefully you've already been exposed to this in Gen Chem. So there's a simple way to sort of verbally express Hammond's postulate, and that's just to say that the transition state looks most like the species on either side that is closest in energy to it. Okay, and so if we just consider protonation to form a primary carbocation, sorry, a secondary carbocation, and then trapping to give product. If we're interested in thinking about the geometry of this transition state, okay, what we say is that it's going to resemble the species that's closer in energy to it. In this case, it would be the carbocation. It's going to look more like the carbocation than like the starting alkene, okay? And so if I wanted to put this in sort of more formal terms, the way it's typically written is we say a reaction, if it is endothermic, if I'm going uphill in energy, we say that these have late transition states. Okay, they look more like the products or the intermediates that follow the transition state. Okay, so from the perspective of the Hammond postulate, an intermediate is the same as a product. We're just referring to what follows a specific transition state. Okay. And then exothermic reactions, we say have an early transition state. They look like starting material. Okay, so we can apply that to the second step of the reaction here. You can see that for TS2, it is much closer in energy to the carbocation than to the final product of the reaction. And so TS2 resembles more closely the carbocation, okay? And you might be, you could sort of intuit this if you think about it from the perspective of sort of molecular sort of rearrangements. If I've got a very high energy species, the carbocation has a planar geometry. It's going to take less energy. It's going to sort of resemble, because it has a lot of energy, the transition state where I've got partial bond forming or bond breaking occurring, okay, which is always destabilizing, okay, is going to be closer in energy to that high energy species. It's going to look physically more like that high energy species, okay? And the corollary is true going to the right. So as I go to very stable products, the transition state starts to resemble more and more the starting materials or the intermediate. And so the technical terms for this are sort of late and early. Late means it looks like products. Early means it looks like starting materials. If I wanted to draw what the transition state, what TS1 might look like, it would be something like this. So you would basically have you would have bond forming to the hydrogen of the HCl, and the pi bond would be breaking, and you'd have accumulating positive charge at that internal carbon. Okay, it would look something like that. I'll try to do some modeling to give you guys some pictures because it'll be clear as day when you see this. Okay. All right. So right. So that's basically all that I want to say on this on the HX addition reactions. Looks like we're a little bit ahead of time, but that's okay. Okay, I'll just add one more. Yeah, I have one more comment, which is this idea of the rate determining step. So so the rate determining step of a reaction is defined as the step in a reaction with the highest energy transition state. Okay, and so for these HX additions, it was always that first step is going to be the highest energy step. Okay. And when we're measuring the activation energies, we always measure from the starting materials. So this is delta G double dagger TS1, and this is delta G double dagger TS2. Okay. And so the first step can be higher in energy as it is for these HX additions. There are also reactions where the second step is higher in energy, or the third step, or whatever. It doesn't necessarily have to be the first. Of course, if you have single step reactions that proceed through a single transition state without any intermediates whatsoever, you don't have any, there's only one there's only one transition state that is the rate determining step by default. But so in this case, delta G double dagger TS1 is the rate determining step. And so what does that mean? Practically, it means that that energy is what determines the overall rate constant of the reaction. So because the delta G, double dagger for TS2 is lower in energy, as soon as you form that carbocation intermediate, it is immediately consumed by chloride. It is consumed faster than it is formed, okay? And this has important implications for being able to detect intermediates. So it's very difficult to detect carbocations because they are rapidly transformed to product. But in terms of the kinetics and thinking about the rate of reaction, we're always going to look to our highest point on the reaction energy diagram. And that is the delta G double dagger that we are concerned about in terms of the rate and things like that. And that is what is referred to as the rate determining step. So okay. And again, I just want to emphasize, it's not necessarily the first step. So you can have transformations, for example, where you go from A to B, and then up to C, and then the barrier to TS2 is higher. Okay, so the second step in this case is the rate determining step, and we'll see reactions where that type of scenario manifests. Okay, so in this lecture we talked about carbocation stability, hyperconjugation, and a little bit about kinetics. And so that'll wrap up the lecture for today, and I'll see you guys on Friday, or if you haven't watched this before then, on Monday. Okay, bye.